I'm very excited to talk about some of the work that my group has been doing, which broadly focuses on modeling and mitigating communication bottlenecks for large model training at scale. And essentially, a lot of the things that I'll talk about really fit within the theme of this workshop. And feel free to interrupt me in the middle of the talk as well. Of course, I'm also happy to take questions towards the end. I'll also try to go a little fast so that we can get you guys to lunch soon. So let me start with a few trends that all of you are probably very, very familiar with, right? So the first is, of course, you've probably all seen versions of this chart already today. So the size of AI models. Specifically here, I'm plotting the size of transformer-based models, which are really the building blocks for tools like ChatGPT and Bard that we're all, of course, very, very familiar with. So the models are really large, billions of parameters, touching close to even trillion parameters. Another trend is, of course, on training data sets, right? So our models are only as good as the data that we train them on. And in fact, one of my students went and asked ChatGPT, this was like when it was GPT 3.5, what its training data set size was, and ChatGPT said it was 570 gigabytes. When we asked the same question to Bard, it said it was 1.56 trillion words. So of course, naturally, a lot of training data, which starts stressing our systems, right? So on the system side, there's very interesting implications, where on the compute side, you have zeta scale of floating point operations. And Moore's law is kind of dead or at least stagnant, right? So we cannot simply rely on our CPUs getting faster and faster to get us the processing we need for training and serving these models efficiently. The other challenge is around memory, right? So you cannot, so just to fit these models today, especially some of these large models, you need multiple devices and multiple memories, right? So if you think about, let's say, a high-end GPU today with, even 32, 64 gigs, even 128 gigs of memory, but we're talking about billions to trillions of parameters here. So one example is even for GPT-3 with 175 billion parameters and using a lot of, additional optimizations like zero, which I'll not really go into, you need 16 just to fit a GPT-3 model, 128 just to fit a 1 trillion transformer model. And this is just to fit the weights. I'm not even talking about all the training data. So naturally, this means that you really, really need, tens to hundreds of devices. And finally, if you have, of course, so many devices, naturally that leads to communication. And in the context of ML training, this leads to tens of gigabytes of collectives. So this is, a number that's often used. So if we take a look at, trying to train GPT-3 on an older NVIDIA V100 GPU, you would need 355 GPU years. So this is basically means that, distributed training is inevitable, which means we need to shard our model and data across multiple accelerators. And I'm going to use the word NPU to be very generic. For the most part today, these are GPUs, but as you've seen, several companies are also building ASICs in this space, right? So I'm trying to be very generic here. So in fact, when we asked ChatGPT how many GPUs were needed to train it, it said thousands of GPUs, and Bard said thousands of TPUs. So this has led to a third trend, which is very exciting, which is the fact that there are a lot of emerging high-performance computing systems being built specifically for AI. So these are some examples, right? So Google's Cloud TPU, NVIDIA's HGX boxes, Intel's Habana Gaudi, Meta's Xeon EX, and even startups like Cerebras with their Andromeda systems. So from a 100-foot view, most of these AI platforms look something like this, where, this is like a classic node where you have a bunch of servers with their CPUs, with some memory, with their NICs, and you also have this NPU or DNN accelerator sitting here. Of course, there's many of these in a node, and then all of these nodes are connected together. So two key aspects separate these platforms from, let's say, just conventional server systems. So the first is, again, these very customized accelerators for AI, which are NPUs at the endpoints, and a lot of customized network fabrics, both within the node to scale up and across the node to scale out. And a key challenge that that we are focusing on is data movement here, which is both from the accelerator to memory and of course within these fabrics. So a lot of our work has been trying to understand the design space. So I come from a computer architecture background, and we've been trying to understand how do you build such systems very efficiently? How do you build the accelerators? How do you build the fabrics? And how do you kind of scale? And so in order to do that, we've been trying to understand the overall hardware software co-design space for distributed AI. And again, this is kind of preaching to the choir, and I'm sure many of you are working, on one or more aspects of this stack. But just for setting the context, let me just briefly talk about this. So we've tried to divide up the entire hardware software co-design stack into 5 components, which I'm describing using 5 colors. So the green part is something we call the workload layer, which includes the model itself, its parallelization strategy, the communication policy and pattern, and some framework level scheduling. So think of this as decisions that are today taken at the level of PyTorch or TensorFlow, right? Then below that, on the pink color is what I'm going to call the system layer. This is really where the communication mechanism and scheduling comes in. So this is entities that would be handled by libraries like NVIDIA's Nickel today, or Microsoft's MSCCL, or AMD's RICL, and so on. So collective communication libraries. And then the light blue and the dark blue parts are the compute and the memory. So think of this as your device. And then the orange part is the network, which has its own software and hardware stack. Like it could include things on the software side, like the messaging and transport layer, if you're using RDMA and so on, and getting down to the actual endpoint design, network fabric, network topology, and low-level details like network implementation. What is your buffering strategy, congestion management, flow control, and so on. So this is going to broadly also mirror the outline of my talk. I'm actually going to talk about 2 things today. So the first is going to focus on some work we've been doing on collective communication scheduling. And the second is going to focus on how do you model and simulate this entire stack in a multi-fidelity manner. How do you think about workloads, and how do you think about modeling these systems? So that's kind of the key outline. So I'll start with the first piece, where specifically I'm going to talk about scheduling over multidimensional network topologies. All right. So with that, let me start by again motivating the importance of communication in distributed ML, and I'll do that with a very simple yet powerful example. So here, this is some data we got from some simulation experiments we did, where what we were trying to look at was I believe I don't have it on the chart. This was ResNet. We were looking at the time it was taking to train it. And we were trying to see what would happen if our GPUs became, 2x, 4x more efficient, while the communication fabric remained the same. And so the blue part is the compute time. The orange part is the exposed communication. This is the time that cannot be hidden behind compute. So ideally, you would like to hide all the communication behind compute, in which case, this is perfect, right? All your accelerators are operating at full utilization. So here what you can see is, as your compute becomes more and more efficient, communication starts becoming exposed. So this is really the motivation, where we really need to start thinking about optimizing communication, especially since our compute is becoming very efficient. If you followed the recent trends from NVIDIA, and even AMD's announcement yesterday with their latest GPUs, these are extremely efficient. Hundreds of flops, and even things like support for sparsity rate. So a lot of things that are making compute very efficient start stressing the communication more. So let's now try to understand what exactly this communication is in DL training, and then we can start optimizing it. So this is just a snapshot of the co-design space I showed earlier, but the communication can be understood as following, right? So if suppose you have a DNN model and you come up with some parallelism strategy, you could use tools like deep speed for this, and or flex flow, where you come up with some strategy. It could be data parallel, tensor parallel, some 3D parallel strategy. Once you have that, typically this is where a collective communication library comes in. It extracts the specific collective pattern, and I'll talk about this in the next few slides. Then for the pattern, we identify what is the collective algorithm, and then we schedule that over the network fabric. And like this is really where the communication is coming, right? So at this point, you are actually sending network messages. So let's try to dive in here a little bit. Let me try to explain what the communication is before we start optimizing it. So just for some quick background, again, if I'm, let's say, doing data parallel training, then, and I'm going to model the entire compute as just matrix multiplication, right? Every layer is effectively a matrix multiplication. So what you do during data parallel training is you take the input sample. So this is the input matrix. I'm sharding it across, let's say, 2 devices. So half the inputs have gone to this device, half of them have gone to this device. And the weights get replicated. So each device gets a copy of the model, and gets some partitions the inputs. I do this matrix multiplication and get partial outputs. So in the forward pass, this is the forward pass, there is actually no communication between the devices, because everybody has the full model. They just have partial inputs and they're just running inference on their input samples. So forward pass is actually is easy and quite optimized in data parallel training. But when we come to the backward pass, now here you're computing the input gradients, then you're computing the partial weight gradients because you only have the partial inputs. And since you have only the partial weight gradients, you actually need to synchronize them to compute the full weight gradients. And this is because ultimately for the next iteration, everybody needs the full copy of the model. And this synchronization is actually done via a pattern called all reduce. And then of course, you also compute the input gradients, basically, right? So if you look at the flow in the backward pass, this is what it looks like. So at each NPU, I compute the input gradients and the weight gradients. Then I synchronize the weight gradients within all reduce, and so on and so forth, all the way up to here. Since each layer is independently computing its weight gradients, this communication is non-blocking. At the very end, though, I have to make sure all of this communication finishes before I start the next iteration. So at that point, it becomes a little blocking. Okay, so I've talked about all reduce. Let me kind of dive into what exactly that is. Right? It's one of the most dominant patterns in distributed training. It's common, it's natural in data parallel, and it also occurs in some model parallel training strategies. And really, mathematically, all it does is the following, right? So if I have 3 devices, 3 NPUs, and they have some partial weight gradients, what happens after an all reduce is, if I have partial weight gradients for, let's say, this is the pink part is a subset of weights. I have partial gradients 1, this has 2, this has 3. After the end of the all reduce, this gets added up here, this gets added up here, this gets added up here. So everybody gets a full copy of all the weights. That's basically what an all reduce does. And mathematically, you can break it down into 2 steps, which are called reduce, scatter, and an all gather. So reduce, scatter, as the name suggests, is a scatter and a reduction. So you reduce this and scatter it. So after reduce, scatter, all the NPUs have part of the weights, but they have like the updated copies. And after an all gather, which is just a broadcast, everybody gets the full copy. So this is an animation just showing that 3 NPUs, 3 partial weight gradients. After the end of the reduce scatter, I have added this up. NPU1 has part of the weight gradients, but it has part of the weights, but it has added up the partial gradients to get the full gradients, and so on and so forth at NPU2 and 3. And then an all gather is just a broadcast. So at the end, I get the full copy of the weights. So this is an all reduce, and this is again just one of the patterns that is common in distributed training. So this is just a slide trying to show several collective communication patterns, and I'm going to keep using the word pattern here because again, some of these terms are not very precise in the community, but by pattern, this is just kind of the mathematical operation that I'm doing, where again, as I said, there's simpler patterns like scatter, gather, reduce, broadcast. We just talked about all reduce, which is reduce, scatter plus all gather. There's also all to all that often occurs in some model parallel training strategies. And these are all patterns, and there can be diverse algorithms to implement a specific collective pattern. So collective communication algorithms you can think of them as routing algorithms within the network to implement your collective pattern. And again, collective communication libraries typically implement these different algorithms. So for example, for an all reduce, there are several algorithms: ring, direct, halving, doubling, Raman siphoner, double binary tree, and so on. And given a network topology, typically there exists one of these algorithms that is the most efficient for that topology. So this is what is called a topology aware collective algorithm. So let me give an example. Suppose I have four NPUs connected physically in a ring. So I have four GPUs that I've connected in a ring, and I want to perform an all reduce. And in this case, I'll perform what's called as a ring-based all reduce. So a ring algorithm on this physical topology. The physical topology is a ring. My algorithm is also a ring. So the name being the same because it is topology aware. So the way the ring-based all reduce works is as following. So suppose I have four devices here. I'll actually break up my weight matrix into four parts and break it into, in some sense, four components. And once I've done each of them has computed the partial gradients and it's time for an all reduce, the way this algorithm will work is as follows. So node 1 will forward gradient 1 to node 2, node 2 will forward 2 to 3, 3 will forward 3 to 4, and 4 will forward 4 to 1 as shown here. Then they will add it up to the local copy of the gradients, and then 2 will forward this updated 1 to 3, 3 will forward 2 to 4, and so on. Again, add it up with the local copy, and then again forward this here, add it up with the local copies, right? So as you can see, in 3 steps, the reduce scatter is done. Everybody has completed a reduce scatter. Now they all have the full weight gradients, but for just a partial subset of the weights. And then I do an all gather, which is simply a broadcast. So again, same thing. I just take my copy, forward it to my neighbor, take this copy, forward it to my neighbor, and so on. And so at the end of an all gather here, my all reduce is complete. So basically we went from here to here, right, with this ring based all reduce. So what you'll notice here is that if I ask you, was there any congestion in the network at any point, the answer is no, right? In every step, what you noticed was I had exactly one message going on the links. And it was beautifully orchestrated where every cycle there was only one message on the link. There was no congestion. And in fact, every cycle, all the links were completely occupied. So I had 100% utilization. So this is actually perfect. So this is why this is the perfect algorithm for this topology. But what if my topology was not a ring? It was something else. So suppose I could connect all of these GPUs together in with a fully connected network. Then in fact, a ring-based all reduce is actually slow, it taking n steps. And in fact, it's only using the link to my neighbor. But here I have links connecting to everybody. So I can actually do something more efficient. In one step, I can do a reduce scatter, have everybody add up the gradients. And in one step, everybody does an all gather. So this is just an example of another topology-aware collective algorithm. So as I mentioned, there's several topology-aware collective algorithms. For rings, there's a ring-based algorithm. For a fully connected topologies, the direct algorithm that I presented. Similarly, for a switch, there is something called a recursive halving doubling algorithm that I won't go into, which basically, kind of does this reduction in pairs, basically, or does it in log n steps. And each of these algorithms is, again, very optimized for this topology. Unfortunately, though, these simple topologies are insufficient to scale to thousands of nodes, right? So if I wanted to build a cluster with 1,000 GPUs, I couldn't connect all of them up with just a single ring. That will be too slow, right? Very large diameter. This will not be scalable. And similarly, a switch, right? Switches can have maximum today 3264 ports. I can't have 1,000 ported switches, right? So this basically means that I really need more sophisticated topologies to actually build larger systems. So if you look at some of the systems today, they do use more sophisticated mechanisms. So here is, a few examples from NVIDIA, AMD, Intel, and Meta. And from the perspective of how they are connected to each other, they actually use, typically some traditional technologies or techniques like, in this NVIDIA's case, you have a bunch of NV links connected to an NV switch, followed by, another level of scaling via InfiniBand. Intel Habana uses some custom NICs, followed by Rocky, which is RDMA over converged Ethernet. Similarly, Meta uses a hybrid of NVLinks and Rocky, and so on. And there's also systems that are using more and more exotic technologies. So Google TPU actually uses photonic interconnects to scale out. Cerebrus uses a wafer scale technology to really build a large node followed by a custom topology they call SwarmX. And then Tesla and Tensorent have actually gone with mechanisms for trying to build very, very large packages with chiplets and scale using chiplets followed by traditional mechanisms. So the point being that in order to design next generation platforms, you actually end up having a lot of different networking technologies that are being used today. So you have all the way from chiplets and advanced packaging and wafer scale to some custom rack scale interconnects like NVLinks or XC-Links, and InfiniBand Ethernet or even optics. So what that means is, and there's no silver bullet. What you'll see is there is no one technology that is winning, which is why all of these technologies are being used in some form or the other across systems today. So what we really, I think, envision and expect is in the future, you will have systems which will, let's say, have some set of NPUs connected on package with some advanced technologies, packaging technologies like interposers. Then you build these packages, connect them up via rack scale interconnects to create nodes, and then you use kind of maybe create these larger pods, and then finally use scale out using NICs. And again, this is just example bandwidths that are for these different technologies that we found from literature. But the key takeaway is that future systems are expected to have multiple network dimensions and typically different bandwidth and latency characteristic per dimension. Right? So this kind of is really going to the motivation of what the problem that we're going to solve. Right? So our future clusters or AI clusters, AI platforms are expected to have multidimensional network topologies and diverse bandwidths. And now the question is, how do I run a collective algorithm on a topology like this, right? Conventional collective algorithms are really optimized for very simple topologies. So just as an example, suppose I have a 2D torus as my topology. And if I try to run a ring-based algorithm, logically, I can actually map a ring onto this. So in fact, today, if you were to give an arbitrary topology to a collective library like Nickel, it will just try to run a ring-based collective. But you can already see that using a ring-based collective here is underutilizing several links in the network, right? So there are several links that are just not being used. So in order to address this, there's been some prior work. Essentially what you do once you have more multidimensional topologies is you try to run collectives in a hierarchical manner. So let's say, in step one, I do reduce scatter over the dimensions or the rows. Then I do a reduce scatter across the columns. Then I do an all gather across the columns. Then I do an all gather across the rows. So this is what's known as a hierarchical collective. There's been systems like IBM's Blue Connect that have actually demonstrated how this works. And in this case, again, there's no network congestion. That's great. But even though all the links of the network are utilized over time, unlike just running just a simple 1D ring over this, at any instant, you can see only 50% of the links are being utilized, right? So this is not actually very efficient in terms of link utilization. So this is where collective scheduling comes in. And this is going to be the piece that I'll talk about next, right? So so just to kind of recap what I mentioned so far, I'm trying to run all reduced collective pattern because I have a data parallel training strategy. I'm trying to figure out the best algorithm for it. I'm going to use this hierarchical algorithm where across each dimension, I will first run the all reduce. Across the dimension, I'll still use I'm going to still use a ring-based all reduce, right? So this arrow is trying to say across these 4 GPUs, I'll still use rings. Then I'm going to use the rings across the columns and then back to the rows, right? So I do a reduce scatter across the first dimension. Then I do a reduce scatter across the vertical dimension. At this point, I've done a complete reduce scatter. Then I do an all gather across the vertical dimension, then an all gather across the horizontal dimension. So the challenge with this, as I mentioned, is now link utilization, right? You will notice that while I'm doing one of these communication, these messages on one of the dimension, the second dimension is just idle. So this is quite inefficient. So what I'm going to do first is let's try to pipeline, right? Instead of just running one message at a time, let me actually run multiple all reduces. I have a large matrix, right? And I obviously have to do a reduction across the entire matrix. Let me actually pipeline it into multiple independent chunks so that I can, utilize these better. So the baseline static pipelining scheduling, which is used today, is essentially that, where I actually pipeline my all reduce into, in this example, let's say 4 colors, like four messages. So the green one does a reduce scatter here, followed by a reduce scatter here, all gather, then all gather here, then the yellow one, then the orange one, and then the pink one. So while this is good, I can see that this dimension is now being completely utilized, right? Every step, I'm going to send a reduce scatter on my on the first rows. Then while this reduce scatter is traversing the next network, next set of links, I'm going to send another reduce scatter, another reduce scatter, another reduce scatter, right? So I'll pipeline this to keep filling in, the links. So while this is great for getting full utilization in the first dimension, you can notice that the second dimension is still underutilized. And so this is the problem we're trying to solve. So how do you manage and how do you address load imbalance across these different network dimensions? And there is something very subtle here that I want to now explicitly point out, which is the fact that unlike a regular, network message, which is just traversing the network, one key characteristic of an all reduce here is the fact that the size of the message changes as you traverse the network, right? Remember, a reduce scatter is actually doing a reduction. So when you go from the first dimension to the second dimension, you're actually sending a smaller message. When you do an all gather again, you're, at that point, the message size increases, you're doing a broadcast. And when you do the final all gather, again, you get the full message, which is why in this example, in fact, what I'm showing is exactly that, where in this example, I'm assuming that the first dimension actually has more bandwidth than the second dimension. I send a 64 megabyte reduce scatter here because this goes across the 4 NPUs and does just a reduce scatter here. This message size decreases to 16 megabyte as I traverse the next dimension. So even though the next dimension has lower bandwidth, it is still faster than, this box here. So that's why this box is, smaller. It's 16 megabyte. Once I finish this reduce scatter, I have an all gather, which is just 4 megabytes now. This becomes 16 once I finish the all gather. And finally, here I do a 16 megabyte all gather, which becomes 64 at the end, right? So at the end, of course, everybody has the same size matrix, but through the network, the message sizes are changing, which is a very, very interesting and challenging phenomenon now, where I'm trying to design a network where my bandwidths are variable and the message size also changes. And this gets exacerbated actually once you have more sophisticated network topologies. So just to kind of show an example, suppose I have a 3D torus. This is actually very similar to what Google employs in its TPUs. And I do the same, let's say, a multi-dimensional all reduce, where reduce scattered across the local, then the horizontal, then the vertical dimensions of this torus, followed by all gather on the vertical, horizontal, local. If you look at the pipeline stage, pipeline delays across these. So even if I have assuming in this case all the links are equal bandwidth, you'll notice that again, there's a lot of idle time, especially as I go to the higher dimensions of the network. I'm just waiting and my links are idle because of this phenomenon of, all reduce, right? So uneven pipeline stages that are causing network underutilization. So to summarize what I've said so far, right? I break up my all reduce into multiple chunks, and the chunks, perform reduce, scatter, and all gather in order. But I get into a challenge of network load imbalance. And this is actually interestingly because of 3 reasons, which are part of this entire co-design stack. And these are kind of different parts of the stack. So the fact that the chunk size changes across stages is an algorithm constraint. Right? This is just all reduce, which happens to keep changing the size of the message as I go across stages. I have hybrid bandwidths across the different dimensions. This is a technology constraint. Given my physical technology constraint, there's only so much bandwidth I can drive per dimension. And I have static scheduling of the chunks across the dimensions, which is, kind of a decision of the collective library, right? And together, this is basically leading to underutilization. And so this chart is trying to quantify the impact of this underutilization. So if I show runtime and I show different topologies, I think the thing I'm trying to show is on average, if I just run an all reduce over a multi-dimensional topology, you'll notice that I'm only getting about 53% average utilization of my links because of this challenge. So to address this, we did this work that we published last year called Themis, which was basically built on this interesting insight that mathematically there is no explicit dependence on the order of the network dimensions. So mathematically, there is no reason why I should always do all reduce in this manner where everybody first sends messages across the first dimension, then the second, and the third. Intuitively, the reason we do that is the first network dimension has the highest bandwidth, right? So in most cases, the first network dimension is all your NV links, let's say, followed by InfiniBand. And you would naturally want to send your large size messages on the first dimension because that's where the highest bandwidth is, which is why schedulers work with that with that algorithm today. However, the problem with that, as we just showed, is the other dimensions actually become underutilized. So instead of doing that, let's actually do a more clever load balancing. Let's actually try to send the chunks in different schedules across the network depending on the network load. And so this algorithm that we came up with works with all reduce, reduce scatter, and all gather collective. So the idea is the following, where we are, so remember that this was the baseline scheduling where I am, sending the all reduces in this manner, the green, yellow, orange, and pink with reduce scatter here, all gather here, all gather here. Instead, what Themis does is something like this, where suppose I start with this, green all reduce, it does a reduce scatter here. Then the second, then let's say the second all reduce is also scheduled here, the orange one. Then when it comes to the third all reduce, the yellow one, instead of starting it here, I actually started from the second dimension. So I actually started from the lower bandwidth dimension. So this obviously takes longer. Then, the green one finishes here, the orange one finishes here. This one does the second, phase in this dimension. The pink one again gets started here. So this is a toy example, but what it's trying to show is by doing this scheduling in a greedy manner, I'm actually able to, unlike the previous case where this was completely idle, I'm able to utilize the overall network bandwidth better and finish faster. So I essentially use different schedules for different chunks. And so in this work, we actually, did a greedy strategy. We would just look at the dimension, the load on each network dimension and decide what the strategy is. And the paper actually has more details if you're interested. So I won't go into the specific algorithm in more detail. Okay, so just to kind of, again, repeat the point so that it's clear. So instead of doing the all reduce in a very static manner across a multi-dimensional topology, the basic idea is simply to come up with a greedy scheduling. And so this is the overall architecture of the Themis system. So this is the collective, library with the algorithm. We have our own custom scheduler now, which essentially, tries to get the load, it basically tries to measure the load of the network in each dimension. And it has a inbuilt latency model because the algorithm itself is very deterministic, right? We know exactly how long it's going to take given the bandwidths. We can actually come up with an optimizer internally in the scheduler and then start sending the chunks to the network. And this is just a snapshot of evaluations. I won't go into full details here, but what we basically did was we simulated it using a simulator, and I'll talk about the simulator in the next part of the talk. We evaluated several different topologies. So 2D, 3D, 4D topologies with, different technologies, right? So here, for example, there's chiplets connected together in a package, then some, package-to-package links and so on with different bandwidths per link, different sizes and so on, different latencies. And we essentially, across this suite, we first ran just the all-reduced micro benchmark. And we saw that, you can see here that the average utilization with Themis was now close to 100% for all the networks, which basically, allowed us to get from on average 56% in the baselines to 95%, which just meant for the all reduce itself, we were getting about 1.7x speed up, which when we ran the full workloads translated to lesser exposed communication across the different examples. And on average, we saw, training time go down by about 1.33x. All right. So that was the just a glimpse into, how we can optimize communication scheduling, right, in this multi-dimensional co-design space. But this is really just one part of the stack, right? Like here we assumed everything else was fixed. The network was fixed, compute was fixed, memory was fixed, and parallelization strategy was fixed. But in a lot of cases, we would really like to co-optimize. And so this is where the second part of my talk is going to talk about some very interesting infrastructure we are building to enable multi-fidelity design space exploration. And the motivation for this really comes from two parts. So the first is, is to identify some of the limitations for co-design today. So this is really, the cycle of co-design that is deployed in practice, right? So suppose I have a system that's deployed in practice. Let's say it's the Google TPU or an NVIDIA HGX. I observe some behavior in production. Then I try to reproduce that behavior, right? Maybe I saw that the communication is slow or my all reduce is not very efficient. I try to reproduce it via some representative benchmarks, right? So micro benchmarks to stress test the system. I identify some bottlenecks, and then I try to design a new system, right? It could be, when I say system, it could be like replace the hardware or maybe some new software solution. And then I try to design and evaluate it. Then I finally implement it and test it with some benchmarks, and then, deploy it back in scale. And then, as my workloads evolve, again, observe behavior. And kind of this co-design loops is how things are implemented in practice. But there is a big challenge today, which is the fact that running like full end-to-end workloads is extremely challenging, right? I mean, production servers today are costs like 100K to 100K, right? And this is especially hard for folks in academia to actually participate in this. And even within industry, you'll be surprised, a lot of teams are like, it's very hard for us to really get access to like the full production cluster, right? So you need to be able to do this co-design without having to run full benchmarks. It also often requires full, cross-domain expertise, right? I mentioned this co-design stack. So really to get, performance optimization, you need to understand the software and hardware, which becomes very challenging. It also becomes very difficult to isolate specific bottlenecks if you're running the full workload. And it becomes very hard to keep up with the pace of AI innovations. As your model changes, suddenly you have to re-optimize the entire stack, run it on the production system and so on. So this is a big challenge on the workload end today. And on the actual modeling and simulation end, there is the classic, challenge of accuracy versus speed, right? So if you have a very detailed simulator, it's very slow. If you have a very simple model or simulator, it might not be very representative of the actual, full system. You also typically end up binding to one ecosystem or one simulation ecosystem. You're using Gem 5 or SST as the simulator. And, a lot of times you have, and especially if you're industry, you have some proprietary tools you want to use, and some you want to use some open source tools. It's often hard to mix and match. So that's one challenge on the co-design space. The other challenge is, of course, that the space itself is very complex, right? There are different requirements for different kinds of models. So this is just a chart showing recommendation versus LLM models. This is just trying to show, how the compute, memory, bandwidth, network bandwidth, latency characteristics are different. This is a chart I got from, a talk that Meta had given earlier this year. So there's a lot of different requirements for different kinds of models. There's different parallelism strategies. So, you can vary the model data pipeline parallelism strategies, and you can come up with very sophisticated strategies. There's different kinds of compute accelerators that exist out there. You could be using CPUs, GPUs, or a swath of ASICs that are coming out. On the memory side, especially with technologies like CXL, you can start building very diverse memory architectures. And of course, on the network side, we just saw how you can have, multi-dimensional networks. So what this means is, as you have more and more sophisticated systems and, strategies, you can often keep varying, like moving between systems that are compute bound to memory bound to network bound. So it really becomes very important to be able to, model and study this efficiently. So how do you actually navigate this entire large scale codependent design space? And this is where we've been, over the last, I would say, like 5 years now, we've been building this infrastructure called ASTRA-sim, which is a simulation infrastructure for modeling this end-to-end stack. And it kind of tries to do a one-to-one modeling, and I'll describe this in a few more details in the next slide. So the basic idea behind AstroSim is to be able to model this system, but the key design principle is that it wants to model and simulate these systems with varying degrees of fidelity. So one of the key enablers is the idea that it has a bunch of different APIs with which you can plug in different external tools. So the idea in AstroSim is, instead of building one big simulation infrastructure for modeling this Codesign stack, you can have your own independent models or simulators, or even like real emulators for different pieces, and we will allow you to plug them all together to model a full system, right? So for example, you might have your own GPU simulator because you're trying to study a GPU, and you can plug that in while use whatever we provide for the network fabric, or vice versa. You get some real numbers from a real GPU, and you want to study, well, what happens if I were to connect these GPUs up together via fabric A versus fabric B. You can plug in those compute numbers through our APIs and then simulate what the rest of the system does. So that's kind of the high level idea, and we have a reference implementation that's available, and this is the website. So let me now just very quickly go through different parts of the simulation infrastructure and start wrapping up my talk. So I want to so I'm not going to go into full details, but I just want to give you like a quick, whirlwind tour through the infrastructure. So one of the very key pieces of the infrastructure is how we represent the workloads. And this is kind of a piece by itself. So it is, so from the workload perspective, what we've been working on is this notion of execution traces. So execution traces are really just hierarchical DAGs which capture the nodes are really different compute and communication operators. So let's say this is a compute operator, which is, let's say, just a matrix multiplication. Once the workload is sharded, the communication operator could just be an all reduce, for example. And we also have, other compute operators related to timing and so on, and then different tensor objects. Then the edges are trying to capture control and data dependencies, and you can also build higher level abstraction. So again, without going into full details, essentially we're trying to capture the execution of the workload as a graph. And the idea is that we are trying to model the performance of the workload, not like the exact functional behavior, right? So we don't want to capture the precise execution of the model. We want to capture the key operators that are going to lead to performance and communication operations. And this is trying to be ML framework agnostic. So the idea, again, just to kind of give you, explain this another example, is the following, right? So if you have an AI model, we are trying to capture, we want to run this model on a real system, capture the exact workload in a distributed manner via this execution trace, and then start maybe performing some platform agnostic and platform dependent transformations and then execute it. So the way these execution traces can be thought of is, you could either have a pre-transformed trace, which is really the original model, or you could have a post-transformed trace which has some transformations that have been applied, or you could run the model on an actual system and profile it and get that. Or you could, and this is actually something that we worked on with Meta and have enabled. So today you can go to PyTorch. There's a feature called PyTorch, execution graph observer, where you can actually collect the execution trace on your system along with the timing information, like how long it took to run this. Or you can also try to synthesize these traces. This is another thing that we've been looking at. So this is an example of some of these workload traces, right? So this is, for example, this is actually just a pipeline parallelism strategy where you can see that, essentially each node is just doing compute communication in a pipeline manner, and this is a more sophisticated trace. So this is this effort where we are trying to create this ecosystem where you have these production workloads, you collect these traces with timing information. We are so this is all proprietary. Different companies can do this for their own use cases. And then we start building a more open community-driven infrastructure for analyzing the traces, synthesizing the traces, visualizing them. And then you can use them either to run them or replay them on a current system. So you can essentially allow, traces to just get replayed. So you don't have to run the full workload. You just take the trace, replay it, and try to, reproduce maybe some bug or try to identify some internal system challenges. Or you can take this trace and simulate it on a future system using a simulator like AstroSim. So that's kind of the Chakra piece, right? So the Chakra is really a workload representation that we are using as the input to AstroSim. But as I mentioned, AstroSim is just an example. You can actually, and in fact, we're working with different, collaborators who are using these same traces on their own internal systems or on their own internal simulators. So then what AstroSim does is, given this trace, it will try to parse it, identify all the operators, send it to the system layer. The system layer is where, you are specifying the collective communication algorithms, right? Again, how do I implement all reduce, all the things I mentioned, ring-based, direct, halving, doubling, and so on, and the different scheduling policies. Is it baseline, is it Themis, and so on. Then there is, then we kind of have the actual system layer, which will identify the different operators and then pass them on to different network simulators, compute memory and network simulators. And this is really the key idea behind AstroSim, right? So AstroSim really is a glorified traffic generator. Given the workload and given the collective, implementation, it will start generating traffic for compute memory and network, right? So from a network perspective, it's going to inject and receive traffic. And this is where we can plug in different kinds of network simulators. So the idea is there is a common API, which is just implementing the fact that I'm sending a message, receiving a message, scheduling a callback, and so on. And then you can now plug in different kinds of network simulators. They could be open source, they could be proprietary. You can decide the level of detail in which you want to model different kinds of behaviors depending on what you're interested in. And so today, in fact, we actually have 4 network simulators that are implemented using the network API, and they are again trading off fidelity to speed. So we have a very simple analytical model that's the fastest, but obviously not the most accurate. Or you can plug in like the NS3 simulator that really allows us to model RDMA congestion control, but it's naturally slower. But they work seamlessly in a plug-and-play manner. And there's also additional, proprietary simulators that some of our collaborators at AMD, Alibaba, and HP Labs are using. So that's the network part. Similarly, on the compute part, you can plug in compute simulators of varying degrees of fidelity. Same idea, right? You want to identify the compute time, and just basically, if you have a given compute, the compute simulator tells you the time. And just like, for network, we have different simulators with varying degrees of fidelity and speed that are being implemented in practice. And similarly, we also have a memory module in AstroSim. This is to actually study, more emerging memory architectures like disaggregated memory architectures using CXL and so on. This is something that is not fully developed, but kind of work in progress. So let me put it all together, right? So how does AstroSim work? So the idea is really the following, right? Suppose I have a system today and I want to study what would happen if I were to have a new network fabric, right, in the next generation, but I have the same GPUs. So this is what we are trying to do. So let's say, this is my Chakra trace. It tells me that in today's system, this is the compute, this was of this type, this is the time it took, and it led to an all reduce, with this size, and this is the time it took. Suppose I want to model a system with a new network with the same GPU. What AstroSim would do is, for the compute, it will just extract the runtime from the trace. That's, let's say, 10 microseconds in this example. For the communication, instead of just extracting the time, it's actually going to simulate it. So it's going to identify the all reduce algorithm you want to use. Maybe you want to use this hierarchical ring-based all reduce in this future system, and you have your scheduler, again, right, all of the things we talked about. It's going to simulate them in detail. Through the API, it's going to send this to a network simulator. It could again be different simulators depending on how detailed you want your simulation to be. And ultimately, it will boil down to some time, right? So after all this, you will get some time that it took for this communication operator. And then AstroSim's job is now to see, can I overlap, or how much of the compute and communication can I overlap, depending on the dependencies that the trace told me about. And in this example, maybe I'm able to overlap some part of the compute with communication, but this part is exposed. And this is really the bottleneck, right? So at the end, I'll know that, well, if I use this future network, this is an exposed communication. And then you can decide to kind of go back and re-optimize, right? Again, the beauty being, you don't have to run like your full workload every time. You can just operate with this trace and play around with, different levels of fidelity for compute and communication. So to kind of summarize this part, these are the key features of AstroSim. We model this entire co-design space via plug-and-play APIs for different, simulations frameworks. We model arbitrary workload and parallelization strategies as part of the Chakra trace format. We model system-level behavior. It supports large-scale, multi-dimensional network simulations, and it can run various, compute simulation backend, right? So this is just an example of the kinds of systems we can model with these GPUs connected with some multi-dimensional communication fabric and potentially some disaggregated memory fabric to memory pools. And this is actually having a lot of cool external impact that I'm very excited about. So the Chakra part, right, the workload traces is something that has been adopted by ML Commons. So ML Commons is the entity that maintains benchmarks like MLPerf. And I'm actually a co-chair of a working group that is trying to work on standardizing the format of these traces. How do you collect them? We already have some support in PyTorch. We're also working with Google on support in TensorFlow and JAX. How do you replay this on real system or simulate this? And can we then eventually, we want to get to a point where we create a benchmark suite of these traces that we release to the community. And on the simulator end, AstroSim has had several tutorials, and we have like a growing user base of companies, startups, academics, and so on. And again, if you're interested, feel free to check out the website and get involved. So I want to just now wrap up by just quickly acknowledging some of my current, former students, postdocs, and collaborators who've really driven a lot of the pieces. I mean, I just presented all of this work, but it's really been driven by many of these fantastic collaborators. All right, so finally to conclude, a lot of supercomputing systems are being designed today specifically for AI training and serving, and communication is really a big challenge in large model training. And there is an optimization opportunity here, though. Unlike traditional networks, here once the model and the parallelization strategies known, the communication patterns are quite deterministic, which means you can come up with very clever ways of optimizing them and getting better efficiency from your systems. And co-design across the workload system and network actually offers very, very high opportunities for speed up and efficiency. So in that domain, we are working on two pieces. There's the Chakra execution trace work, which is really an open graph-based representation for the workload execution. It enables isolation of compute, memory, communication behavior, and offers an ecosystem for benchmarking. And the AstroSim simulator is modeling the various aspects of the co-design stack and allowing us to mix and match performance models for compute, memory, and network. So with that, thank you all for the attention, and I'm happy to take a few questions.